Okay, hello people. I'm Dr. Larmore, as you know, and today I'm going to talk about Huffman's algorithm. Now, the problem is the deficient binary code generation. So let's first talk about Morse code. Morse code has dots and dashes, and E, being the most common letter, has the smallest code string, namely just a dot, while Z, being the least common letter, has a long one, namely dash, dash, dot, dot. So you'd think that this would be a binary code because there are two symbols, but there aren't. There are really three symbols. Here, for example, dot, dash, dot, 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 dash, dot, dash, dot, dash, dot, dot, is ambiguous. Now, it could be translated as lifted and also as rival. Now, what's really wrong with Morse code? Well, nothing really. Morse code is not two letters, it has three letters. Dot, dash, dot, and space. But it's not a prefix-free code in that sense, because you notice, for example, that this code string is L, and it has a prefix, which is R, which means as you read these string, when you get to this point, you don't know whether to stop or not. Actually, here you could stop and make it an E. Here you could make it an E, an A. Here you could make it an R, and here you could make it an L. You just don't know where to stop. And the reason is because some strings are prefixes of other strings. All right, we would like to have a binary code. It's called a Huffman code. It's a binary code. It's prefix free. And the letters have equal cost, meaning that 0 and 1 both cost the same amount to transmit. But each letter has some kind of frequency, like E occurs much more often than Z or whatever. And what we're trying to do is to minimize the expected cost of a message using that alphabet with those frequencies. Let's give a quick example here. Here is an example of a prefix-free code for the letters A, B, C, D, E, F. Now, if I want to encode the word bead, I get this string of zeros and ones. And it's length 13, so the cost is 13. Now, let's imagine that our alphabet has these frequencies. E is the most frequent, then A, D, B, C, F. And we can design a code that is more efficient for that frequency. And here is one such code. Notice that the most common letters have the smallest strings, while the least common letters, C and F, have the largest code strings. And now when we code the word bead, it has length only 9. And in general, for an arbitrary English message, this particular code, well, actually this doesn't have enough letters. We need one that has 27 letters, 26 for the alphabet and 1 for space. But if we continued with this idea, we could find a code which is optimal for English language's messages. But, all right, let's look at this particular frequency here and show you Huffman's algorithm. Now, Huffman was a student working under an actually relatively famous professor. And the professor, back in a very long time ago, asked the students to find an efficient code, prefix-free code, binary code, for an alphabet with an arbitrary distribution. And Huffman, who was a mere student, came up with this algorithm, which was better than any previously known algorithm for the problem. And the algorithm is also extremely simple. In fact, it's greedy, and it's so easy to implement, it's kind of hard to believe that it wasn't known before. Anyway, here is the algorithm. If we sort the letters by frequency, which I did here, from increasing frequency, then the algorithm takes O of n time. Of course, you might say, well, it takes n log n time to sort them, but I said if they're already sorted. All right, now what we do is we look at these frequencies, and we think of these as leaves of what we call the Huffman tree. And we combine leaves, we combine elements together to form internal nodes. So we take the two smallest nodes that are still available and combine them to form an internal node here. Now at this point, the nodes 3 and 3 are available, and we can combine them to form a node of value 6. Now likewise over here, the two most common nodes, the two smallest frequency nodes are 6 and 5. Now we have an 11, an 8, and a 10. We can combine these to form 18, and we combine these two to form 29. This is an example of a Huffman tree. It's a binary tree where the leaves are the alphabet. And at every node there is a frequency, which is the sum of the frequencies of the letters at the leaves under that node. Now, what we will do here is, in code, use this tree to create a code. What we do is we stop this completely arbitrary, whether we call this 0 or 1. So I'll just say the left one is 0 and the right one is 1. We now have defined a binary prefix-free code for that alphabet. As it turns out, it's actually, well, is it the same one we have over there? Perhaps. If we shuffle the letters around, it might not be the same, but as long as the lengths are not different, then the code is optimal. So therefore, if we then write down what the code strings for these letters are, what we do is for each letter, we start here, we follow from the root down. So A is 1, 0. And B is 0, 0, 1. See it? If C, that would be 0, 0, 0, 1. And D would be 0, 1. And E would be 1, 1. While F would be 0, 0, 0, 0. Well, as it turns out, that's exactly the code that I put up before, which is not a coincidence, because I first drew this tree and worked it out before I put those code strings up. This particular code is definitely optimal. And what that means is if you take an average message consisting of these letters, so in other words, you pick each letter with a probability proportional to that frequency, and pick a bunch of letters, and then work out the length of the message, which is your cost, then the average length of such a message would be smallest with this code. Now, of course, if I exchanged E and A here, I would get 1, 1 for A and 1, 0 for E, and that doesn't matter. It would still be an equally good code. So there are many optimal codes for each example. But for each code, there is a binary tree here. And the binary tree has the property that the nodes with the highest frequency are closer to the root. Now,